Chapter 7 introduces the concept of stoichiometry with a discussion of the balance of the essential elements for life, including nitrogen, oxygen, sulfur, and of course carbon. It then dabbles into how carbon is contributing to climate change, and so I thought I would use this as a springboard into a larger discussion of that subject that also ties together things that we've been learning in previous chapters. And in the process, you'll hopefully start to understand some of the science behind climate change, and this will hopefully help you to think critically the next time you hear about this in the news or in some political statement. And so first, let's talk about what it is to be a greenhouse gas and what the greenhouse effect is. I shared a little song. It's kind of silly, but it gets the point across. That was made, sometime in the 1950s or 60s, I think. So the idea of a greenhouse effect, and here's my little greenhouse. So here we are in the winter time, and it's very cold outside. So here you have Frosty the snowman outside, and inside the greenhouse we have plants growing. So why is it so warm in the greenhouse? Well, as you heard in that song, we have short wavelength energy coming in from the sun that penetrates through the glass of the greenhouse without a problem, and it gets absorbed in all of the materials that are inside the greenhouse, the soil, plants, and whatnot. But then they get re-emitted as long wavelength heat energy or infrared radiation. These have a typically longer wavelength. And because they're low of energy, they can't penetrate back out through the glass, so they get bounced back and reabsorbed, and basically it traps the heat in that sense. So the glass is trapping the longer wavelength heat energy waves, but the short wavelength solar radiation, that gets through without a problem. Now, in the context of how molecules can behave like the glass of a greenhouse, that has to do with the fact that bonds have vibrational energy that can absorb and reflect. They're not just rigid sticks that I might show in a model. If I were to draw a bond between two atoms, it stretches, and it also comes in on itself. So there's energy in and out. There's also energy of it bending. And this vibrational energy has a certain wavelength and frequency. And remember back when we studied the Bohr model of the atom that explained how certain wavelengths of light were absorbed for a particular element, or absorbed wavelengths were also emitted when you ignited it in a flame. Well, the same principle is happening here. If the wavelength of light is equal to the vibrational energy associated with these bonds, then those bonds will actually be able to absorb that energy. And not just absorb them, but also reflect that energy back, or re-emit it. So in the case of carbon dioxide, CO2, and we know what the Lewis structure of carbon dioxide is, we'll put that again. In this case, these bonds, these double bonds in carbon dioxide, they have a vibrational energy that is in the infrared range, meaning that it matches those long heat waves, the infrared energy that's re-emitted. Now, what does that mean in the context of the planet? So here I've got our little planet Earth down at the bottom, and let's put a little atmosphere in here. And in the atmosphere, of course, we have lots of molecules. It's mostly nitrogen and also oxygen, and the rest, far, far less than 1%, are other gases such as carbon dioxide. So it's really not there that much, but all that nitrogen, all that oxygen, those bonds have their own unique vibrational energy wavelengths, but those don't match infrared radiation, so they do nothing to trap that heat from being re-radiated out into space. Carbon dioxide, those bonds match the infrared radiation. So when you have the solar radiation coming in from the sun, short wavelengths, high energy, right? Those come in and hit the Earth, and they get re-radiated as the long heat waves, just like we have in the greenhouse. But when they hit carbon dioxide, they don't go out into space. If carbon dioxide wasn't there, they would just go out into space, and we would die a cold death on an icy planet Earth. It's the carbon dioxide in the atmosphere that actually keeps us warm. It's actually very, very good that we have carbon dioxide in the atmosphere because it keeps us warm. And it does that by absorbing the radiation and reflecting it back to the planet. So the problem isn't that we have carbon dioxide in the atmosphere. The problem is that it's getting too much. And the problem with it getting too much is that that's what's contributing to the increase in global climate temperatures. And there's a difference between talking about the climate and just talking about the weather. So let me dispel that for you right off the bat. Weather is just what's happening outside today or tomorrow or this week. Climate is something that you can see over a long period of time, and it's the change that's happening over a long period of time. Over the years, right, going back from the late 1800s to modern day, you see that we have a global temperature. Now this is in Fahrenheit, and we're correlating that with the concentration of carbon dioxide in the atmosphere. Now that's measured in parts per million. It's how many particles there are for every million particles of air molecules. Okay, so this is simply just showing that there's a correlation between increasing global temperature and increasing carbon dioxide levels. But it's more than just a correlation, because we also have the physics of this chemistry being that the vibrational energy of the bonds in carbon dioxide match that of the heat energy infrared radiation, and so it acts as a greenhouse gas. Now let's look at this increase in carbon dioxide levels in a much more detailed way. This is a Keeling curve, named after Dr. Keeling. When he was a graduate student, he had the fantastic opportunity to do his research in Hawaii on top of Mauna Loa, and basically tracked what the carbon dioxide levels were for a couple of years. That was back in the 60s. Now at first, it actually didn't make sense. You see this jaggedness here, and if you were to actually zoom in on just one cycle, you'd see that it tends to go up in April and then down again in October and then back up again. And when he first started taking a few data points, it didn't really make sense. They were kind of all over the place until you took enough data points throughout the year and then correlated that year after year. You saw that it was in fact cyclical. Turns out that it correlates with the different rates of photosynthesis during the year. Now, what is photosynthesis, you may ask? Let me remind you of that reaction. Photosynthesis is something that plants do. They can actually make carbohydrates. They make glucose by combining carbon dioxide and water to make C6H12O6. That's glucose. And they make molecular oxygen, which is what we breathe. So that's really, really nice. So this is photosynthesis. We do the reverse of photosynthesis. We metabolize glucose, C6H12O6, and turn it into energy. This is a combustion reaction. The byproducts are carbon dioxide and water. So this is what we call cellular respiration. When photosynthesis is very, very active, it tends to pull a lot of carbon dioxide out of the atmosphere. And so each year it goes up, down, up, down, up, down. But if you now extend that over a much longer period of time, you see that overall curve is rising. Now, all of these animals on the planet who are metabolizing glucose and breathing carbon dioxide, right, that's creating more carbon dioxide in the atmosphere, but that's not really a problem. What are some of the other sources of carbon dioxide production? Well, of course, the big one is burning of fossil fuels, of course. So here's octane for gasoline, C8H18. Let's do the combustion reaction for octane. And if you balance this equation, I'm not going to go through the process, I'll just show you what the coefficients are of the balanced equation. 16 moles of carbon dioxide for every 2 moles of octane that are combusted. There's also burning natural gas, right? That's methane. That's another combustion reaction. It doesn't produce as much carbon dioxide. There's others as well. Now, what do we have to get rid of that carbon dioxide? Well, as I mentioned, we have plants. They do that by photosynthesis, so that's good. But of course, on top of that, we also have deforestation. That's a pretty big problem on the planet as well. So, you really can't win. All right, but how big of a problem is this really? So for that, we need to go and look historically. And when I say historically, I mean look over the past 800,000 years. So that's what's shown down here. And in that time, we can track what the atmospheric levels of carbon dioxide are. First, we assume that the production of carbon dioxide and also that its ability to be removed from the atmosphere was constant all of this time. But then it's actually measured by looking at pockets of air that were trapped in glacial ice. And we get the age of those pockets. That comes from radioactive decay from certain isotopes, like krypton-81 and uranium-238. Beryllium-10 is another one. We do that by watching their radioactive decay. So scientists can measure how old these air pockets are very, very well, and then you look at how much carbon dioxide there is in them, and you see a different kind of cycle. If you now look at the x-axis, we're talking about thousands of years. Here's 700,000 years ago, 600,000 years ago, and you see these ups and downs. These are due to the ice ages, and when it's a warm period, these are what we call the interglacial periods. All right, now this is real data. This isn't made up. And you see, for over 800,000 years, by analyzing things this way, you see a very consistent cyclical pattern. It goes up, it goes down, okay, but it never really gets above 300 parts per million. It's only until very, very recently that we started seeing a change in this trend. And it started around 1760. This corresponds to the dawn of the Industrial Revolution. That's what's happening here. And now, on the Keeling curve, we're just looking at the past 50 or 60 years of that curve. So for over 800,000 years, it didn't really get above 300 parts per million carbon dioxide. Look where we are now. Now we're over 400 parts per million. When it really only fluctuated for all that time, I didn't tell you about the low. Okay, the low here is really a little bit lower than 200 parts per million. It's not fluctuating much beyond 100 parts per million from the ice ages to the interglacial periods. And now we've already doubled that. And in fact, we're much higher than that. Okay, I just Googled it, and in 2018, the parts per million of carbon dioxide in the atmosphere was 407. So that's where we are a couple of years ago. Now, there's a term you may have heard of called the carbon threshold. The carbon threshold, this is like the point of no return. Considering how stable things had been for over 800,000 years, and now just in the past 100 years or so, we've skyrocketed, and it just keeps climbing. It just keeps on going. The carbon threshold is that point that after that, no matter what we do as a global society, we won't be able to rein that back in. We won't be able to reverse the effects, and overall, the global climate just gets warmer and warmer, and it never gets back to these older, more comfortable times. Most estimates now put that point of no return is at about 450 parts per million. Now we're already pretty close. We're already over 400. Now we still have a chance to do something about this and get things going back the other way. But most estimates say that if we don't do anything, we'll reach that point of no return by around the year 2040. Right? That's not too far away, folks. And that's why there's been such a big drive for green energy and policies that curb global warming industries and things that try to rein in the gross production of all of these greenhouse gases. So yeah, that's pretty scary, but let me end this story on a happier note. Some of you might recall that back in the 1970s or 1980s, we had another global issue that was just as great, and that was having to do with holes in the ozone layer. Now, ozone, that's something that we took a look at the Lewis structure for. Let's put that up here. Ozone, those bonds, now, of course, now we know it's not a double bond and a single bond, but we know that that's actually in resonance, but let's not talk about that right now. These bonds, these oxygen-oxygen bonds, these have a vibrational energy that are in the ultraviolet range. So ozone, O3, is responsible for protecting us from very, very dangerous ultraviolet radiation that comes in from the sun. And if you have a hole in the ozone layer, that means all those ultraviolet rays get through and cause biological damage. So this is a big deal. And it turns out that the science showed that this hole was caused by other chemistry going on in the atmosphere having to do with a collection of molecules called CFCs. CFCs, that stands for chlorofluorocarbons. And you've seen some of these. I've showed you some models. Things like dichloro-difluoromethane, and a host of others. These are used as refrigerants in air conditioners. They're also used as propellants in aerosol cans. And there is a huge correlation and a lot of science behind this. And the scientists were saying, look, if you keep using these aerosol cans and if you keep air conditioning using this technology, you're going to just keep expanding these holes in the ozone layer. And it's going to be a huge crisis for all of the life on Earth because all this ultraviolet radiation is very, very dangerous and damaging. So the good news is the global community at that time listened to the science. They didn't doubt the science. They didn't deny the science. They didn't call the science a hoax. They understood the science and they said, you know what? We need to change our industries. Yes, industries changed. Some new jobs were formed and industries were transformed. And folks, I got to tell you, this problem was fixed. The global community was able to fix this problem. The holes that we found in the ozone layer are no longer there. So there you go. There is still a happy ending, perhaps, in store. So that gives you something to think about.